Alright, so today we're going to be taking a look at a little bit of thermal physics. So starting off, let's see, I think I've got these in a slightly different order, but the problem that we've got says gas in a container expands at a constant pressure of 21 atmospheres. So first thing to note, constant pressure, that means this is what type of process? Double check your notes if you're at least watching this as one of my students. Constant pressure processes are called isobaric processes. And as we've discussed in class, it tells us that pressure, hey, look at that, is constant, but it also gives us the equation that the work done on the gas, put into the gas, energy going in, I should say, is equal to negative P delta V. So those are things that we know just from saying that we have a constant pressure. Hey, look at that. It's at a pressure of 21 atmospheres. Ugh. But find the work done by the gas if the initial volume is 5 liters and the final volume is 10 liters. Okay, so they give us a pressure in atmospheres, 21 atmospheres. That's a whole lot of pressure, but sure. And they give us an initial volume of 5 liters and a final volume of 10 liters. Now I know in class we preferentially used cubic meters, and we will continue to do that here. My apologies that we don't have a question that is using the units that we're used to. However, this is something that you want to get used to. I know many of the chemistry classes love to use atmospheres and love to use liters. The problem is, if we simply plug those things in, then we end up with weird values that end up not equating to joules. And we want an answer, work, in joules. So, first thing we're going to do is we're going to convert these. Well, 1 atmosphere equals 101,325 pascals. I'm going to do something that we did very briefly at the beginning of the year, but we're going to set up a unit conversion. Best way to do this is to start off with an equation, a true statement. And here's what I'm going to do. I want to get rid of atmospheres, so I'm going to want atmospheres on the bottom. So I'm going to divide by 1 atmosphere. That's going to cancel this out. And I need to do the same thing over here, 1 atmosphere. My units are gone, and I now end up with this. 1 equals 101,325 pascals divided by 1 atmosphere. This is 1 with no units. Now, why that's important mathematically and conceptually, many of you may be thinking, I know how to convert units, you just put this in there. You're going to find that later on, when you don't have a regular unit conversion, you can still do this same thing. Say, for instance, if I were to ask you how many people could fit in a car, and each person takes up half a cubic meter, and there's 3 cubic meters in there, we could actually do this, although that's a bad example because people don't have a perfect 1 packing factor. Ignore that, but we'll see some of that later on. In short, this is how I go about converting units. It may seem longer than what you're used to, but I can assure you if you get used to it, you can start converting things that you wouldn't normally think that you'd be able to. That being said, what I'm going to do is I'm going to take 21 atmospheres, and I'm now going to multiply it by 1, which is 101,325 pascals. We call this, I learned this from a teacher a very long time ago, we call this a special 1. It's actually 1, but it's special because it looks a little bit different. The important thing is, since this is 1, I don't change a value if I multiply it by 1. It stays the same. It might look different, but it will be the same value. Just the same as 100 pennies is the same value as $1. Or 12 inches is the same value as 1 foot. They look different, but they are in fact the same. So 21 times 101,325, and we end up with a laughably large, but great, 2,127,825 pascals You're welcome to probably take this to 3 significant figures. We call that 2,130,000. That's fine. I'm going to leave this for the time being. So we've got our pressure. This equals 2,120, let's call it 8,000 pascals. I'll round it to 4 significant figures just so we have less issue there. All right. Here's another one where we get a little bit crazy. I'm going to go ahead and give you the conversion factor on this, but we're going to change 5 liters. We want to get rid of liters and get it into cubic meters. Now, technically, I'm doing the same thing up here. I need a special 1. 1 cubic meter is actually equal to 1,000 liters. It's one of the conversion rates that I actually know, but that's fine. 1 liter is probably the size of, say, a drinking bottle. This is a little bit less than 1 liter. Actually, noticeably less. According to this, it's 547 milliliters. So it's about twice this, but a cubic meter is very large. It turns out that there are 1,000 liters in 1 cubic millimeter, or a cubic meter, sorry. So we end up with a volume of, well, 5 divided by 1,000, so that's 0.00, move this 3 spaces over, oops, 1, 2, 3, so yeah, 2 zeros. It's been a long day. Doesn't hurt to double check because I don't want to lead people astray. Yep, 2 zeros. We can also do the same thing for 10 liters, but 10 liters is going to then become 0.01 cubic meters. It'll be twice that. Now that we've got that, I'm going to rewrite them down here because we're almost done. Pressure equals, we said 2,128,000 pascals. And our volume, our initial volume, is 0.005 cubic meters. Our final volume is 0.01 cubic meters. And we're looking for the work done in this isobaric process. So the work done by the gas, it's a small distinction, but we're going to talk about that, equals negative P delta V. Now the work in is the work that we're putting into the gas. In this case, the gas is actually expanding, so it will be releasing energy. So we're actually going to find the work out. We're going to put a negative in here. But first, let's start and find the work in. The work in is going to be negative 2,128,000 pascals times delta V. Delta is final minus initial. It's okay to say that it's change, but you must remember it's final minus initial when you're actually solving these. 0.01 minus 0.005 cubic meters. I'm going to write the units on the outside just to make things a little bit easier. All right, let's see. So I'm going to take that. Now remember, this is cubic meters. This is not cubed. I'm just taking delta V, so it's 0.01 minus 0.005. The meters cubed is the units. It's not affecting the numbers there. Okay, times 2,128,000. If I've done this correctly, the value I'm getting is the work in, the work that we're putting into the gas in this process is negative 10,640 joules. But they're not asking for the work that we do on the gas that's being put in. They're asking for the work out. So it's the same thing, except a negative. The negative here tells us that we're not putting energy in, we're taking it out, and the question is asking us for how much work, energy, we get out. So we basically drop the negative. I get 10,640, and that's pretty much what we're looking at, okay?